1.18 is a bit of a nightmare to read, so let's go over this very slowly. Starting with the first sentence, very roughly speaking, quantum mechanics is relevant when the de Broglie wavelength of a particle in question, h over p, is greater than the characteristic size of the system. So the de Broglie wave is basically a method of characterizing solid matter as a wave. So normally in classical mechanics, we would not traditionally sort of mix together those two concepts. Where in classical mechanics, we're used to sort of defining a solid matter as particles and then waves as their own separate thing. However, the de Broglie wave gives us a way to sort of link those two together. So as a result of that, a solid particle would have a wavelength that is associated with it, and it would be described using h over its momentum, where h is the Planck length, or the Planck constant. So quantum mechanics is evidently important when h over p is greater than the characteristic size of the system d. So if the de Broglie wavelength describing the particle is larger than the system, then we sort of start having some weird quantum effects come into play. For one example of this is indeterminacy. So the wavelength, the de Broglie wavelength of a particle, one of the things it describes is the position of the wavelength, or sort of describes the position of the particle. If your wavelength itself is larger than your system, then as a result of that, well, the particle is now technically everywhere in the system, and because of that, there's sort of an indeterminacy. It's not exactly in a specific position in our system, and because of that, we then start using things like wave functions to sort of describe probability densities instead of exact positions. So the next thing we're given is that in thermal equilibrium at Kelvin temperature T, the average kinetic energy of a particle, defined using momentum instead of velocity, is going to be equivalent to 3/2 k times T, where k is the Boltzmann's constant. So as a result of that, if we sort of isolate for p in this expression, then the de Broglie wavelength in terms of all of these values is going to be h over p, where if we solve for p in terms of everything here, is going to be equal h over the square root of 3mkt. So moving on, the purpose of this problem is to determine which systems will have to be treated quantum mechanically and which can be safely described as classical. So what we're apparently going to do is we're going to find ranges for possibly any of these variables, most likely temperature, for which a system is either going to be quantumly mechanical above or below a certain temperature, and classical on the other side of the spectrum. Let's start right away with part A. So solids. Solids are made of many atoms sort of locked together into some sort of lattice, and we're told that the lattice spacing in a typical solid is roughly d equals 0.3 nanometers. So let's write that down right away. D is going to be equal to 0.3 nanometers. And the next thing we're told is we want to find the temperature below which the unbound electrons in a solid are quantum mechanical. And let's deal with that right now and ignore everything underneath. So we want to find the temperature below which the unbound electrons in a solid are quantum mechanical. Well, let's start right off by sort of writing out the condition for quantum mechanical processes to even occur. So what we need is that we need the de Broglie wavelength to be larger than the size of the system, and we've defined the de Broglie wavelength to be this. So h over the square root of 3, and then the mass is going to be an electron because we're dealing with electrons in our lattice. So mass, and we're going to, whoa, that is horrible. Okay, mass sub E, so to denote the mass of an electron, multiplied by K, multiplied by the temperature, where K is going to be our Boltzmann's constant, has to be greater than the distance of, or the size of our system, D. So, evidently all we have to really do here is we just have to solve for T to find the range for quantum mechanical viability. So let's start right away just by squaring everything here. So h squared divided by 3 times the mass of our electron times the Boltzmann's constant times temperature has to be greater than d squared. Now, if we just solve for T, then what we're going to get is that T is going to be less than h squared over 3 times the mass of an electron, me, times the Boltzmann's constant times d squared. And so this is sort of our range. So now we just have to plug in constants. Planck's constant is 6.626 times 10 to the negative 34th in joules times hertz, which is the units we're going to be using. The Boltzmann's constant, using kilograms and Kelvin and meters, is going to be 1.38 times 10 to the negative 23rd. If we then plug in d using meters as 0.3 times 10 to the negative 9th, because we're using nano. And then finally, the mass of an electron in kilograms, which is 9.109 times 10 to the negative 31st, we're going to get that this is roughly equal to 1.29 times 10 to the 5th Kelvin. So let's add some text. Temperature must be below this for electrons to behave quantum mechanically in a solid. And before we actually sort of understand what exactly this means, let's just very quickly solve the second part of part A first before we sort of look at what the significance of this is, because the moral does tell us the significance, and we will explain everything after we're done with part 2. So next, we want to find the temperature below which the nuclei in a solid are quantum mechanical instead. So instead, what we're doing here for nuclei is we're going to be doing the exact same process, but instead of the mass of an electron, we're going to be using the mass of a nucleon, k d squared. And for the mass of a nucleon, well, in this problem, they specifically ask us to use silicon. Well, silicon has an atomic mass of 28, and if we translate that, it's going to equal roughly 4.66 times 10 to the negative 26 kilograms. So if we plug everything in the exact same as before, but replace the mass of an electron with the mass of a silicon nucleus, this is going to be giving us approximately 2.51 Kelvin instead. And this is going to be temperature must be below this for nucleons to behave quantum mechanically in a solid. And now let's sort of try to understand what actually this implies for a solid. If we look down here, the free electrons in a solid are always quantum mechanical. This is not exactly true. I don't really like the wording here. Are generally quantum mechanical because the temperature cutoff is very high. If we wanted our electrons to behave classically, we would have to raise the temperature by an insane amount, because 1.29 times 10 to the 5th Kelvin is a very high temperature. If you want that in Celsius, you could maybe just add 273 or subtract 273. No, add 273, and evidently that's a very high temperature. So in our everyday lives, for most solids that we encounter, the electrons in that system will behave according to quantum mechanics. In contrast to that, for the nucleons of a solid, the temperature cutoff is extremely low. 2.51 is getting very close to sort of absolute zero, which is the lowest possible temperature we can ever achieve physically. And because of that, most of the solids we encounter in our everyday lives, their nucleons will behave classically. So that is sort of the moral here. In general, the nuclei are not quantum mechanical, whereas the electrons are quantum mechanical. And then the same apparently goes for liquids, which in most ways are kind of the exact same as solids, except maybe the bonds are a little bit looser and they allow them to like slide across each other, with the exception of helium below 4 Kelvin, which does display some very unique properties, but we're not going to go into that right now. But basically, the fundamental idea is that solids typically behave according to classical mechanics, or at least their nuclei do. And since their nuclei are what make up the lattice of a given solid, because of that, the solids that we interact with on a daily basis, for example, an eraser or a ball, they behave classically. We can predict their behavior using classical mechanics. In contrast to that, the electrons in the solid, which we cannot sort of look at physically, or we can't really interact with when we're actually handling something like a ball, those do behave quantum mechanically. However, since we are mainly interacting with the nucleons, as a result of that, solids to us, for all intents and purposes, appear as if they were purely classical objects. In part B, we're asked to do the exact same thing as we did in part A. The only difference now is that we're dealing with gases instead of solids. So the hint we're given is to use the ideal gas law, PV equals NKT, to deduce the interatomic spacing. And I really want to make this, I really want to put some emphasis on this term, interatomic spacing, which is basically the space separating individual particles in our gas. So, evidently this is an ideal gas, which thankfully makes our calculations significantly simpler, but we can sort of make a bunch of assumptions about this ideal gas, and one of them is that each sort of atom in our gas is separated from all the other atoms by an exactly equal distance. So because of that, sort of, if we have this gas cloud, one thing we can say, or one thing we can assume, is that all of the atoms that make up this gas cloud are equally spaced far, or are spaced equally far apart from one another. So let's say something like this. So the distance between the center atom to all these side atoms is, in our ideal assumption, sort of equal. So there's nothing really stopping us from sort of making a cubic lattice. So let's just assume that in our 3D gas, each particle of this gas is sort of contained inside a perfect cube, and all of them are perfectly far apart from one another. Obviously, this isn't true, but since it's an ideal gas, we're sort of allowed to make these assumptions. So in 1D, the size of our system was defined using D. Since we're moving on to sort of a 3D space now, what we can say is that the volume that is occupied by a single particle is going to be equal to D cubed. So if we take the ideal gas law and sort of condense it down and describe it for a single particle system, we can say that P times D cubed, where D cubed is the volume that the atom occupies, is equal to, and N is the number of particles, and since we're analyzing a single particle in this gas, N just becomes 1. So PV cubed is equal to K times T, and if we isolate D, then we get that D is equal to the cube root of K times T over P. Whoops. And from here, we sort of can just solve this problem in the exact same way that we did before, which is sort of the condition that we required for quantum mechanical systems to be quantum mechanical is that the de Broglie wavelength, h over square root of 3m kt, has to be less than the distance, d, which is going to turn out to equal the cube root of kt over p. And now we have just a very simple algebraic exercise of sort of isolating t and solving for it. So in this case, we have a square root on the left and a cube root on the right. So the easiest thing to do here would be to just take the 6th power of both sides. So if we take the 6th power of the left side, we get h to the power of 6, and then 3mkt to the 3rd. And then on the right, if we take the 6th power of a cube root, we get just kt over p squared. So if we sort of do this, then we get h to the power of 6th divided by 3mkt to the power of 3, and this has to be less than kt over p to the power of 2. And from here, we just have to isolate t, and indeed, if we go through this whole thing, we do get sort of the answer that Griffiths expects of us, which is that t is going to be less than this big, messy expression right here. Whoops, I did not want to do that. Apologies. Take this and move it down here, and this is our resulting answer. If we isolated t, we get that t has to be less than 1 over k times h squared over 3m to the power of 3/5 multiplied by p to the 2/5, where m is the mass of our gas molecule, h is the Planck constant, k is the Boltzmann's constant, and P is the pressure of our gas, which is given to us initially because we have an ideal gas at some pressure P.